Okay. Yeah. Before we get started, so yeah, there's one thing that I really have to apologize. Yeah. Last time I realized that I made a minor mistake when I was dealing with indices. Yeah, I'm sorry about that, but yeah. Although this one looked well, but it turns out this index mistake was actually a huge mistake. Uh, so last time, so when I was trying to change the index, so here I tried to change the index from starting from 0 to starting from 1. And in order to achieve this, then actually the sign here has to be not plus, but this guy should be minus, right? So, and minus 1 should be over here. But last time, my bad, yeah, but I actually write down n plus 1 here. So, well, because of this, my summations was somehow messed up. So then what is the right notation? So, well, sorry, but this one should be minus. And so I also, and this guy should be therefore positive. And this one also should be, yeah. So just like this, yeah. This is the right notation. I'm really sorry about this. But fortunately, yeah, well, I realized I made a mistake before I uploaded my lecture notes. So, well, if you go to the PRMS and if you download the PDF file, then you will actually see the right sign notation, right index in that PDF. Sorry about this, but yeah, I really need to fix it. Okay, and thank you for your understanding. And let me get started. Well, so last time, so we talked about the Laurent series. So what is the Laurent series? Well, sometimes you have the analytic function, but your domain of your analytic function may not be simply connected. So for instance, for such cases, such as you have a analytic function, but if your function fails to be analytic at some certain point, in other words, if you have a singular point at some point, then you can actually, instead of getting the power series representation of your function, but you can have a Laurent series representation of the function. The Laurent series is some sort of series, but instead of having only positive powers of z minus z0, but Laurent series also allows the negative powers of z minus z0. So this is the Laurent series, and this is an and bn. So this is what we proved in our previous lecture. And today, so we want to talk about the uniqueness of the Laurent series. So what is the uniqueness of the Laurent series? Well, suppose that you were able to find some series representation of a analytic function on some analogous domain. And in that case, that series representation, so which may allow the negative powers of z minus z0, must be the Laurent series of the function that is being represented by the series. So this is what I mean by the uniqueness of the Laurent series. So the first goal of today's lecture is to prove the uniqueness. And in order to do that, well, first, I will need to talk about the uniform convergence of the Laurent series. So let me get started. Okay. So this is about the uniform convergence. Suppose that I have a, well, I have a series with that allows both positive and negative powers of z minus z0, and say that this guy converges to some function, or well, maybe I will name it by s of z, on which domain? in an analysis domain, say from okay, so let me say this guy is converging to this one on this analysis domain. Then now what I want to do is just choose any two random point. Such that Z1 minus Z0 and Z2 minus Z0 is less than R2. This number, I will name it as R1 and this is R2. So, well, then what is the conclusion? The series converges uniformly to on these closed analysis. Okay. So, well, maybe a nice picture. So, well, I hope this might help you understand the theorem. This is the center of the series, so namely Z0. And this is the analysis domain. So this is D. So therefore, this inner radius is R1, and this outer radius is R2. And I was able to choose two random points on this analysis domain. So this is Z2, and this is, say, Z1. So well, because of our assumption here, the distance from the center to Z1 is less than the distance from Z0 to Z2. Okay, so then the conclusion of this theorem is, under this hypothesis, okay, oh, my picture is not horribly complete, so not that bad, but well, the conclusion is, inside of this, well, this green shaded region is a closed annulus. Okay, good. So on this closed annulus, this convergence is uniform. So this is the conclusion. Okay, all right. All right, let me prove this. So, well, now just let me go, if I go back to your assumption here, then we already know that this series is converging to this guy for converging to this guy, but this S of Z consisting of two terms. This infinite series, I would say this is infinite series number 1, and this is infinite series number 2. And sum of these two infinite series being convergent means if and only if this guy is convergent and that guy is also convergent, right? Both. So this guy converging, or if and only if these two guys, those two infinite series, they both converges. So this is convergent. If and only if this guy is convergent, and this guy is convergent. So okay, So, well, please allow me to change my expression a little bit. So I would say just Bn Z minus, oh, everything raised to the power of n. Okay, so we already know that these two series, they both convergent. So therefore, this guy convergent means, well, and we have chosen two random points from Z1 and Z2. So that means if I plug in Z equals to Z1 or Z2 here, then this one should be convergent. And same is true for this the second infinite series. So if I replace this Z by Z2, then this guy also should be convergent. And oops. And this one should be also convergent. So if I will say Z1. Okay, good. Okay, so now take a look at these two series. So this is clearly the power series, right? The power series of Z2 minus Z0, right? And this, well, now, for if you take a look at this, the second infinite series, this is, I can also say this is a power series, but this is a power series not of Z1 minus Z0, but this is a power series of fraction 1 over Z1 minus Z0, right? And now this is best time to make use of the properties of the convergence of the power series. So, well, so since this guy is convergent and plugging in Z equals to Z2 is also convergent. So therefore, well, this is uniformly convergent. Sorry, this is absolutely convergent. So replacing this by the absolute values. This is also convergent. And this is also convergent. Okay. So I'm going to say this number to be R2. And I will say this number, this entire fraction to be 1 minus R, well, 1. Because, well, yeah, because of this reason. So, well, we have already assumed that this number is R2 and this number is R1. So this is R2 and R1, 1 over R1. Okay. So suppose that my Z is inside of this closed annulus. Then an Z minus Z0, everything to the nth power is but this is well, so since this number is less than R2, so R2 raised to the power of n, and this is And this is also less than, oh, sorry. And times 1 over Rn to the nth power, right? Yeah, so because since we have this inequality, so well, flipping this, well, we also have this inequality already. Okay, so now, so I want to make use of the so-called the Weierstrass M-test. So this, which was a part of the previous exercise, homework exercise. So what is the Weierstrass M-test? So that is, suppose that if you have a series of functions that looks like this, and if each of these guys is bounded by some number, and if this is convergent, then the Weierstrass M-test tells us that this series converges uniform. So that was the statement. So, okay, so therefore, the conclusion is for this closed annulus, just choose any point over here. In this closed annulus, this guy is this summand is clearly bounded by this number, and this summand is closed, obviously bounded by that number. And we already know that this guy is convergent and that guy is convergent. And because of this, so therefore, because of the M-test, so this guy converges uniformly, and this converges uniformly. So everything is converging uniformly. By test, so it converges uniform. Okay, great. So we proved the uniform convergence. So now, what makes this uniform convergence so important? Well, because we have the uniform convergence, so I can try to prove a very useful theorem for the Laurent series, just as we did for the Taylor series. So now we know that this partial sum series sequence z minus z0 and from n to 1, n minus 1, bn z minus z0 to the minus nth power, they both converges uniformly on this closed annulus. Okay, so because of this, for any epsilon, I should be able to find two integers, n epsilon and m epsilon, such that if two indices are greater than these two numbers, then this guy minus this should be less than epsilon, and this one minus that is also less than epsilon. For independent from the position of the point Z from this closed analysis. Okay, all right, yeah. For future purpose, I'm gonna name this guy to be, well, so yeah, last time I believe that I named this guy to be log n of Z, which is the remainder, and this guy to be the difference between this remainder to be the sigma n of Z. Okay. All right. Okay. Now, what I want to do is, so for any closed curve, well, closed and positively oriented, see in this closed analysis, I can actually take advantage of hold on, what is my S of Z? S of Z is this guy. The function that is being represented by this series. So with this one, this guy was S of Z. And I integrate. So I first I multiply this S of Z by some test function. So G of Z is assumed to be a continuous, well, this guy is nothing but a continuous function, which is continuous on this closed curve, C. And I take an integration of this function. And well, then this is, yeah, sorry, I am running out of space. Well, this is the test function. But from n0 to n minus, sorry, I will just copy and paste everything. So plus, what was that? Yes, log of Z, log of n of Z, and plus, and this guy, everything by dz. So this is and dz plus the integral of g of z and log n of z dz plus another integral of test function g of z times sigma n of z, everything by dz. Okay, right. And this is a okay, so yeah, I just ended up with some formulas involving 4 integrations. And what I want to prove here is I want to show that these last two terms, this guy and that guy, they both tend to 0 as n goes to infinity. So, well, how do I know that? Oh, this is very easy. Well, because, well, since we are assuming that this test function, g of z, is continuous on this curve C, so therefore, this modulus of this guy must be bounded by some constant, right? And same is true for this side. And also because of the uniform convergence of the series, well, this rho n of z and sigma n of z can be chosen to be arbitrarily small for sufficiently large index n and m, right? So, well, therefore, this guy and that guy can be chosen. These two guys, the moduli of these two numbers, they both tend to 0 as n goes to infinity. And also the length of this curve is also strictly bounded. So therefore, using the ML inequality, we can easily show that these two numbers tends to 0, right? So this guy and this guy tends to 0. So we're done. And so so it turns out from n0 to infinity, an and dz plus another summation from 1 to infinity and bn and c g0 times 1 over z minus z0. Okay, right. So this is the trick that I proved, that this is the trick that I used when I was trying to prove the integration by term integration and term by term differentiation, right? So when I was trying to prove that, so we used the fact that the series of convergence of series in uniform manner, and I'm actually applying the same trick. So so basically, so technically, so this is an infinite series, and since this convergence was uniform, so I was able to interchange the infinite sum and the integration in this. Okay, so now what? All right, and we have to remember that this equality is true for all such continuous functions on C. So maybe we let 1 over 2 pi times I times z minus z0 and m plus 1. Power raised to the power of m plus 1. But this time around, so m doesn't have to be positive integers. M can be any integer. So m can be some negative numbers too. And also we let the C to be a closed curve or also positively oriented and enclosing the center of series Z0 and contained in the analysis. Okay, so for this function and that function, well, clearly this function is continuous on this curve. So I am safe to make use of this equality. So 1 over 2 pi I times C S of Z, everything, the Z minus Z0, so M plus 1, and dz. is this integral just carries over. Oh, sorry. I must have 2 pi I over here. And z minus z0 n minus m minus 1 and dz and plus over 2 pi I and the integral z minus z0 minus n minus m and minus 1 and dz. Okay. All right. Okay. Now I have to consider some different cases. First, you should remember that if z minus z0, if C is any positively oriented closed curve enclosing this center, and this is m dz, and this guy equals to some 2 pi times I, only if, and otherwise equals to 0, right? So if n is positive, if m is positive integer, then m is n. Sorry. If m equals to k, which is positive, then 2 pi I c s of z and z minus z0 to the k plus 1 is, on this side, then the only non-zero number happens when n equals to precisely k here, right? So this one has to be the ak, right? And if m is negative integer, then if m is negative integer, then this is only true for, if n is minus k, then minus k plus 1 is b, if only non-zero number happens when b equals to k, right? Yeah. If b is k, yeah. So, okay, good, right. Great. Okay. So let me, that was a long argument, but let me just cut to the point. So, I have from the very beginning, so I had this series, so Lorentz-like series defined on this analysis. And it turns out these two coefficients, an and bn, must be in these forms. ak must be just like this, and bk should be also like that. So what do I know from here? So these two coefficients, ak, an, and bn, follows precisely the same as the two coefficients that was given in the Lorentz theorem, right? So this implies that this implies that this is actually the Lorentz series of this function. Okay. So suppose that, suppose that I have a Laurent-like series, converges to f of z on some analysis. Then the series must be the Laurent series of Fc on this analysis. So this proves the uniqueness of the Laurent series. Okay. Let me pause just a little bit, couple of seconds, and please allow me to explain why this theorem is very important. All right. So let me just go back to the very beginning of today's lecture. So, well, once we know my function is analytic, Oops. Yeah. Once we know this function is analytic on some analysis domain, then we know because of the Laurent theorem, we know this function allows this Laurent series expansion centered at this point, Z0, right? This is good. Okay, the question is, how do we get these coefficients, an and bn? According to the Lorentz theorem, in order to find these coefficients, an and bn, all we have to do, we actually need to compute these main integrals. So these infinite main integrals and this infinite main integrals. And a priori, computation of this integral may require a lot of computation power, right? So should be very tedious or very painful. But because of the uniqueness theorem, suppose that we somehow find any such an expansion that represent your function on some certain on this analysis domain, then that means that series representation is automatically the Laurent series expansion of your function. Therefore, you don't need to actually compute these two functions, these two numbers, these two coefficients, an and bn. Okay, so let me show you the importance of this theorem by example. Suppose that I want to find the Laurent series of this function, fz 1 over z times 1 plus z squared on this punctured disk with the center is the origin. Well, a priori, suppose that we cannot take advantage of this uniqueness theorem. Then then the only way to find the Laurent series of this guy is nothing but computing these two integrals, right? But in this case, finding the Laurent series of this function should be doable because we can actually find the series representation of this function using the geometric series, right? F of z is, well, 1 over z times 1 over z squared, but this is 1 over z, and we already know the power series representation of this rational function. This is from n0 to infinity, and minus 1 to the nth, and z to n, right? So this is z2 n minus 1. So this is 1 over z minus z plus z third and minus z to the fifth, da, da, da. Okay? Well, and we already know that this series, that this expansion is true for if z is less, the modulus of z is less than less than 1. Oh, sorry. But in this case, since we should not be including the origin, so this is the correct domain of convergence. And we were able to find a series representation of this function. And the uniqueness theorem guarantees that this guy must be the Laurent series of the given function. Okay. Isn't that great? Yeah. This reduces a lot of computational effort when you try to find the Laurent series. And just one more thing. I want to talk about the maximum radius of the inside and outside radius of the Laurent series. So what do I mean by that? So when we are talking about the Laurent series, then the domain of Laurent series, it must be analogous, right? So that means we have the inside radius and outside radius. We have two radiuses. Okay, we have two radiuses, and for simplicity, let me just please allow me to call this guy the inner radius, and this is outer radius. And in this case, the inner radius equals to 0 and outer radius equals to 1. But this is the best we can do. Why? Because if you take a look at this function that is being represented, then you can actually find three singularities for this function, right? The first singularity is the origin, and the another one is plus I, and the last one is minus of I, right? And you want to find the Laurent series expansion of this function with center equals to the origin. So that means the maximum possible outer radius cannot exceed 1, right? And by same reason, the maximum possible radius of the smallest possible radius of the smallest possible inside radius should be 0, right? Because this is okay. Let me do a couple of more exercises because this is getting very interesting. The same problem. Find the Laurent series of z plus 1 of z minus 1. And we say the center of expansion to be the 0. And on these two analyze z1 is less than 1. Okay, so what do I mean by that? Please let me locate the singularities of this function. I actually have just one singularity at this point when z equals to 1. And here we are trying to find the Laurent series of this function centered at the origin. So therefore, the first possibility is this, right? Centered at the origin. And if you try to expand the outer radius, but outer radius cannot exceed 1, right? So this is the maximum possible outside radius. Oh, sorry. So this is D1. And instead I can try something even crazier than this. Okay, let me just focus on the second domain, D2. So which is still analysis, but this time this analysis is the outside of this unit circle? Well, and topologically, this is still analogous. And if your center of your expansion is the origin, then in this case, your outside outer radius can be arbitrarily large. But however, the inner radius cannot be smaller than 1, right? Because of the location of this singularity. So in this case, there can be only 2 possible Laurent series of this function centered at the origin. Okay, so let me try to find the answer of the Laurent series for this domain. Oops. Okay, first in D1, but okay, so let us focus on this disk domain, D1. Well, clearly there is no singularity inside of this domain. So therefore, my function is, well, completely analytic in this simply closed domain. Therefore, in this case, my Laurent series must coincide with the Taylor series of functions, right? Should not have any negative powers of z to the z minus z0, right? So f of z is the z plus 1 times z minus 1. So, well, this is minus. So allow me to change this guy like this. And so this is z plus 1 times minus and z to the n from 0 to infinity. And by some index juggling happening over here, and it turns out that this is minus 1 minus 2 times from 1 to infinity zn. Okay, so this is not horribly complicated exercise. I guess you can easily do this on your own. What about the second analogous domain D2? Okay, I will try to find this second analysis. I'll also try to make use of the geometric series. First of all, you have to realize that, so this guy is less than 1 if and only if the modulus of z is greater than 1. So this is my original function. But allow me to change its expression a little bit. I will divide top and bottom by z. So I have 1 plus 1 over z, everything over 1 minus 1 over z, right? So 1 plus 1 over z. And considering as the geometric series of 1 over z, so this guy can be also written as, sorry. I will just say from 0 to infinity. And this is true because since we are working on this green shaded domain, and every point on this green shaded domain satisfying this relation, right? So this is also justified. And by playing with some indices, also you can say that this is maybe 1. Okay. Okay. So let me look at this. This is clearly the Laurent series, and it does not contain any positive powers of z. It only contains the negative powers of z. But this is the Laurent series. Okay. The next exercise is we find the Laurent series of function exponential composed with 1 over z on this analysis. Well, also I should mention the center equals to 0. Okay, so, well, originally the exponential function doesn't have any singularity. So I mean, exponential function is an entire function, but since this guy has been composed with a function that has the singularity at the origin, therefore this function may fail to analytic at the origin. So this function actually has the singularity at the origin. So therefore, the inside radius should be 0, right? Now, the question is, how can I get this Laurent series, which is very easy? Well, we already know that this is the power series of exponential function. So therefore, due to the uniqueness of the Laurent series, 1 over n factorial to the z to the minus nth power. So, well, we know that this is true for all complex numbers. And so therefore, this must be true for all complex numbers. But, well, at the same time, this is true for all complex numbers, all non-zero complex. So this is the rule. Okay. The next exercise is, well, even more interesting. Find all Laurent series of one over z minus 1 minus 1 over z minus 2. Okay. So I am supposed to find all Laurent series. Okay, so hey, hold on. Because what do I mean by all Laurent series? Do I have many different Laurent series? Well, because, well, according to the uniqueness of the Laurent series must be unique. So therefore, this exercise is actually asking us to find the Laurent series for different analysis domains, for different analysis. If I draw a picture, then this may help you understand the situation, what is going on here. This is the center, and this is my first singularity at z equals to 1, and this is the another singularity at z equals to 2. And this is the center of the expansion, z0. So, I must have 3 different domains for the Laurent expansion of this function. The first one is the closed disk. Sorry, this is the first one is the open disk with radius 1 centered at the origin, right? And so I will say this is the region number 1. And the second domain is this is analysis domain whose inner radius centered at the origin and inner radius equals to 1, then outer radius equals 2. And finally, the last domain should be the outside thing, so outside domain, whose inner radius is 2 and outer radius is infinity. Okay? So on domain or region number 1, and f of z must be, so this guy is 1 minus z plus, and this is 2 times 1 over. So, so from 0 to infinity, and Zn plus 1 over 2. This is true for the radius of, so this is true for the open disk of this radius 1, and this is true for open disk of radius 2. So, but anyway, in this case, we actually need to intersection of these two open disks. So therefore, it is reasonable to say that this expansion, this expansion is true for an open disk with radius 1 centered at the origin. And simplifying that, we have from 0 to infinity, okay. Well, sorry. Okay. So wait, I don't need to simplify it. Yeah, this is good. Well, and as you can see from here, well, all I can see is the positive powers of z. So therefore, this is actually the Taylor series of given function. But this is completely rigid because, well, inside of this radius, inside of this, there is no thing, so no such a thing. What about region number 2? For region number 2, well, for this region, so I cannot take advantage of this expansion anymore because the radius is, so moduli of the point at this point is greater than 1. So therefore, minus 1, z minus 1 should be written as minus 1 everything times, am I right? Oh, certainly I'm not quite sure about. Oh, okay, yeah. Is it good? Hey. Oh, yeah, this is good. Sorry. Okay, so, and from 0 to infinity, and 1 over z over here, and minus, and 1 over z to the n. So this is minus to infinity. So just like this. And this is true for, and since this expansion is true for when the modulus of 1 over z is less than 1, but in other words, so this is true for all z is greater than, whose modulus is greater than 1. Therefore, on this domain, on the region number 2, yeah, this is complete. So this is clearly true. And also, minus 1 over z minus 2 is still 1 over 2 times yeah, I can still take advantage of this expansion because, well, in this domain, the radius of moduli are less than 2. So therefore, the Lorentz series must be this guy plus this. Oh, sorry. Okay. All right. So in this case, I have a positive powers of z, and at the same time, I have the negative powers of z. So this is also Lorentz series. And finally, in the last region, 1 over minus z minus 2 can be written as minus z1 minus 2 over z. And this is minus, oops, 2n and z n plus 1 for 0 to infinity. And this is true for all z's whose moduli greater than 2. So therefore, on the final region, I have this. Plus this. So this is the Lorentz series for the view of your function at the last radius, so last elements. And it only has the some negative powers of it. So this is how you're supposed to find the Lorentz series. And finding the Lorentz series is, well, considered somehow important in the next section. So when you try the residue integral, well, but this is how we usually find the Lorentz series. Okay. Good. Great. Now let me turn to the next section, which is about the singularities. And zeros. Do you remember the definition of the singular point? Well, in complex analysis, we say my function has some singular point, or sometimes we say my function has a singularity at point z0 if such that so this is my point at z0, and we say my function f has singularity at z0 if, well, first my function should not be analytic at this point. And the condition number 2 is for every deleted neighborhood of this guy, every deleted neighborhood of this guy contains some point at which my function f is analytic on them, right? So this is the definition of the singularity. Okay. Then isolated singularity of f if there is a deleted neighborhood well, epsilon well, of z0 on which f is analytic. So we define the notion of the isolated singularity. Okay, so what do I mean by some singular point, a singular point is isolated? Well, suppose that I have I have a function f, and suppose that my function fails to be analytic at this point. And in this case, each of these singular points must be isolated. Why? Because if I choose my epsilon to be sufficiently small, then I can actually find some deleted neighborhood of each of these singular points. And on this deleted neighborhood, well, my function is analytic at there, right? So in this sense, all the singular points must be isolated. So in particular, suppose that my function has finitely many singular points, then that implies that these singular points must be automatically considered to be isolated. Okay. But there is some exception, like this. Well, suppose that I have infinitely many singular points. Well, and suppose that these singular points have some kind of accumulation point here. Then, in this case, well, this singular point cannot be called to be isolated. Because in this case, no matter how small your epsilon is, but your deleted neighborhood fails to be analytic at this point. Okay. We consider the Churich function, complex Churich functions. The tangent is defined to be the sine over cosine. And well, so can you guess the singularity of this function? It has infinitely many singularities. And these singularities are located at plus minus pi over 2 and plus minus 3 pi over 2. These are all singular points. And are they isolated? Yeah, they must be isolated. So these are all singular points of this function. So they are isolated. So what about this function? So the principal branch of the logarithm function. So this is, so ln r plus I times theta. Here, the r is, r is positive, and this is what we call the principal branch of the logarithm function, logarithmic function. I want to consider, well, I want to talk about the origin of the origin. Is origin singular point of this function? What do you think? Yeah, this origin must be a singular point, right? Because, well, clearly my function fails to be differentiable at the point, so therefore cannot be analytic at the origin. The question is the origin an isolated singularity? No, yeah, obviously no. Why? Because, well, this is, say that this is my complex plane, and this is the domain. And for this point, for the origin, no matter how small your epsilon is, but you can still find some other point and fails to be analytic, right? So this is non-isolated singularity. Origin is non-isolated singularity. Finally, I was trying to come up with some pathological example. 1 over sine pi over z. So what are the singularities of this function? Well, clearly this function fails to be analytic at the origin. So the origin is the singular point of this function. And also, so if n equals to, if z equals to 1 over n, here n is an integer, then, well, then that means my denominator is pi of n times pi. So therefore, denominator equals to 0. Therefore, singular point, right? So this is singular. This is singular. So they are all singular point. Oh, yeah. My picture is really bad. But OK, I know you get the point. Well, Well, in this case, well, the origin is an isolated singular. The origin is non-isolated singular point, right? What about the other guys? What about this point? Is it isolated or non-isolated? And this is clearly not isolated singular, right? So it has infinitely many singular points, but the only non-isolated singular point must be the origin, right? And we will be mainly discussing the isolated singular point this time. Well, later on, we will try to explain something about the non-isolated singular point, but usually in complex analysis, the behavior of a function close to the non-isolated singular point is supposedly has very pathological movement over there. So we will be mainly discussing the isolated singular point. Okay. All right, I guess my time is up. So yeah, I guess this is for today. And thanks for your patience and see you next time.